In this video, we're going to discuss valence electrons and Lewis dot structures. Now let's review electron configurations before we talk about valence electrons. Here we have boron, and boron's electron configuration is 1s2, 2s2, 2p1. Let's start with these two questions. How many electrons are in the very first energy level? Now how would you determine that? Remember that the coefficient tells you the energy level, and then the exponent tells you how many electrons there are. So in the very first energy level, there are 2 electrons. What about the second energy level? So if you take a look, all of this is the second energy level. So we're looking at the exponents 2 and 1. 2 plus 1 is equal to 3 total electrons in the second energy level. So the electrons are divided between core electrons, which are the inner electrons, and the valence electrons, which are the outer electrons. So using those two words, core electrons and valence electrons, the core electrons for boron would be 1s2, meaning that there are 2 core electrons, and the valence electron comes from 2s2, 2p1, so boron has 3 valence electrons. What about chlorine? How many electrons are in the very first energy level? 2 is correct. How about the second energy level? Here's the second energy level. 2 plus 6 is 8 electrons. How about the third energy level? So in the next part, 2 plus 5 is 7. So 2 on the first energy level, 8 on the second, and 7 on the third energy level. So what are the core electrons? The core electrons comes from 1s2, 2s2, 2p6 for a total of 10 core electrons. The valence electrons only comes from the highest energy level, so this is the third level for chlorine, and it has 7 total valence electrons. Valence electrons are found in the atom's outermost shell, in other words, the highest main energy level. The valence electrons determine the chemical properties of an element, and they're the ones involved in chemical bonding, which we will get to in the next unit. And as we learned before, elements in the same group have similar chemical and physical properties, and it is due to these valence electrons. So remember that this unit is all about patterns and it's all about trends. Valence electrons is the same thing. The valence electrons increase in number as you go across a period. Elements in the same group have the same number of valence electrons. You can have a maximum of 8 valence electrons. This is called the octet rule. So all atoms, in fact, want 8 total valence electrons. Why? Because that means that the atom is stable. Remember that the noble gases, they're stable. They don't want to react with anything. They don't want to bond with anything. Yes, you can force those elements to react and you can force those elements to bond, but ideally they don't want to be touched. They want to be left alone. And so all atoms try to achieve that. They want 8 valence electrons because, again, that means that the atom is stable. Now, hydrogen and helium is a different story. So on the smaller atoms are satisfied with 2 valence electrons. So if you take a look at the periodic table, every element in group 1 has 1 valence electron. Every element in group 2 has 2 valence electrons. And then you skip over to group 13, and now we have 3 valence electrons, and then it continues all the way up to 8. Now, all the noble gases have 8 valence electrons, with the exception of helium. Like I said, helium, if you think about it, only has 2 electrons, so it can only fill up the very first energy level, so helium can only have a maximum of 2 valence electrons. For the transition metals, you assume that they all have 2 valence electrons because you're looking at the highest main energy level. Remember that the transition metals, the D sublevel, it drops a main energy level. For example, it goes from 4s2 to 3d10. So the highest main energy level for all of your transition metals is the actual period number. So for example, 4s2,3d10, the highest main energy level would be main energy level number 4. So just to reiterate, the elements in the same group have the same number of valence electrons. Now that does not mean that they have the same number of total electrons. Remember that valence electrons means the outermost, the electrons in the outermost shell, the outermost level. And those are the electrons that are involved with bonding. To represent the valence electrons, we draw Lewis dot structures. These dots represent valence electron. Each dot that we draw represents one electron. So I'm going to use chlorine as an example to go through the steps. So you write the element symbol, capital C, lowercase l, and chlorine is in group 17. It is atomic number 17. It's in group 17. And so chlorine has 7 valence electrons. Now these dots are placed one at a time around the element. Now you actually pretend that there's an invisible box around the element, and you're going to draw the dots around the sides. So 1, 2, 3, 4. And then you go around again to pair them up. 5, 6, 7. And this is the Lewis dot structure for chlorine. Remember that you will not have more than 8 electrons, and for the smaller atoms like hydrogen and helium, you will have no more than 2 max. So let's try some examples. Let's start with the electron configuration of lithium. Lithium is number 3, atomic number 3. Lithium's electron configuration is 1s2, 2s1. Now we use Bohr's model, or the planetary model, to help us see where the electrons are on each level, but you will not be tested on Bohr's model. Okay? So on the first ring that represents the first energy level, we're going to draw 2 electrons, 1, 2. And then on the second energy level, you see that there's only 1 electron in the second energy level for lithium, so we're just going to draw 1. Now the third energy level, there's nothing there. I just copied and pasted the same picture, so we're just going to draw on the rings that we need to draw on. And you can see the inner electrons and the outer valence electrons. Remember the core electrons and the valence electron. So here we have 2 core or inner electrons, and we're not interested in that. We're interested on the outermost electron, which is only 1 for lithium. And the Lewis dot, you write the symbol Li, and we're just going to draw 1 valence electron, so 1 dot. Now, it doesn't matter where you begin, and it doesn't matter which direction you go. Just pick a side, your favorite side, and go clockwise or counterclockwise. Let's do oxygen. Oxygen is number 8, 1s2, 2s2, 2p4. So on the very first energy level, we have 2 electrons. And on the second energy level, we have 6. 1, 2, 3, 4, 5, 6. So how many valence electrons does oxygen have? It has 6 valence electrons. So let's draw the Lewis dot. Capital O, pick a side, any side. This time I'll start from the right side. 1, 2, 3, 4, 5, 6. And that's the Lewis dot for oxygen. Now notice that I'm not drawing it like this. 1, 2, 3, 4, 5, 6. This is not how you draw a correct Lewis dot structure. Okay, you want to make it neat. You want to pretend that there is a box around the element, and you're just drawing the dots on the sides so it looks like that. Okay, you're not putting the dots randomly everywhere. Let's go ahead and do sulfur. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. On the first energy level, we have 2 electrons. On the second one, we have 8. And then on the third energy level, we have 6. So how many valence electrons? We have 6 valence electrons. And sulfur, it will have a very similar Lewis dot structure to oxygen, right? So 1, 2, 3, 4, 5, 6. Now, take a look at the periodic table. Where is oxygen and where is sulfur? Aren't they in the same group, group 16? So they will have the same number of valence electrons. Now, what about neon? We can skip the electron configuration and Bohr's model. Take a look at neon. Neon is number 10. What group is it in? How many valence electrons does it have? Did you say 8? It has 8 valence electrons. The Lewis dot structure looks like this. All paired up on all sides. Okay? Manganese. Let's do this electron configuration real quick. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5. Now, the valence electrons are the outermost electrons on the highest energy level. If we're looking at the highest energy level, we're looking at the coefficients. And we're looking at the highest coefficient number, which is the 4th energy level, not the 3rd. So we're only looking at the 4th one, and how many electrons are in the 4th level? There's 2, and so we write 2 valence electrons for manganese, and the Lewis dot structure would look something like that.